We're looking at using the continuous time Fourier series properties to find the Fourier series coefficients of continuous time periodic signals. So in this example, and really you should have looked at the previous example, the previous video. Normally these are optional standalone kind of example videos, but this one does depend on the previous one, so you want to have checked that one out. And in the previous video we found that the Fourier series coefficients of this signal g of t, which alternates between negative 1/2 and positive 1/2 with a period of 4, are given by this guy here, g of t, Fourier series coefficients, and we came up with this expression. Now we're going to try to find the Fourier series coefficients of this new signal y of t, which is not a square, it's a triangle, okay, but with a period of 4. Okay, so we want to see, is there a relationship between x of t and y of t that we can exploit to do this quickly? And there is a relationship, actually, that if you notice, the derivative of y is equal to g of t. You see that? The derivative is a slope, right? You should have learned that in calculus. And so notice if we look at the triangle wave, the triangle wave has a constant slope from 0 to 2, for example, positive from 0 to 2, and the slope there is rise over run 1 over 2, 1/2. So from 0 to 2, the slope is 1/2. Well, that's what we have for g of t. From 0 to 2, we have 1/2. And then from 2 to 4, the slope is minus 1/2. And that's what we have for g of t. We have minus 1/2. And so it alternates like this. The derivative alternates between 1/2 and minus 1/2. And that's exactly what we have for g of t. So hopefully you understand then this relationship holds. The derivative of y of t is equal to g of t. Okay, so that means that we're going to apply the differentiation property. So let's say that the g of t has Fourier series coefficients ak, and since we used ak there, then we're going to use bk here, and so we're going to try to find the bk's. So now if I take the Fourier series operation of this relationship, then I have, from the differentiation property, I'll write it up here. The differentiation property says that, no, I guess I'll just write it here. We need jk omega 0 times the bk's give us the ak's, right? That the derivative operator is replaced by jk omega 0. jk omega 0, and of course omega 0 is 2 pi over the period, and the period here is 4. So pi over 2. So we've got jk pi over 2 times the Fourier series coefficients we're looking for is equal to the Fourier series coefficients that we have. Okay, again, the differentiation property says replace the derivative operator with jk omega 0, and then the y of t's have Fourier series coefficients the y of t has Fourier series coefficients bk, right? And then on the right hand side of the equation, the g of t has Fourier series coefficients ak. So here's our differentiation property. We're going to write that down. Just make a note that that's the property we use, differentiation property. Okay, so we want the bk's, right? The Fourier series of y of t. So that's the ak's divided by jk pi over 2, right? And notice we're going to have a problem with k equals 0 if we apply this property, right? K equals 0 does not hold. In that case, we have 0 over 0. Who the heck knows what 0 over 0 is? So let's first consider, actually let's just make a note that this is for k not equals to 0, because we can't divide by 0. And so for k not equals to 0, we would have then e to the minus jk pi over 2. So e to the minus jk pi over 2 times sine of k pi over 2 over k pi, and then divided by this mess here. So let's write that out. E to the minus jk pi over 2 sine of k pi over 2 over k pi, then over j, so we pick up a k, and we pick up a pi, and then over 2, so we put a 2 out here. All right, so this is the k not equals 0 term. Okay, so can we simplify that a little bit? I think we can. The j can come up, making a minus j to e to the minus j k pi over 2, sine of k pi over 2 over k squared pi squared. And then you can simplify this further by noting that the minus j then can be written as e to the minus j pi over 2. So I'll let you think about that. Think about the complex plane and so on. So now we have 2 times, and then e to the minus jk pi over 2 times e to the minus j pi over 2 makes e to the minus j pi over 2 times k plus 1. Interesting. K pi over 2 over k squared pi squared. Right? So that looks like the square wave, except the amplitude has changed. We've got these squares in the denominator, and then there's a phase that has been picked up as well. There's this phase offset k plus 1. So now, that was for k not equals to 0. For k equals 0, I'll write over here, I'll write this in green. For k equals 0, you can get this quickly using the analysis equation, or just remembering that k equals 0 is the average value. So if we look at the average value of this triangle wave, it goes from 0 to 1 linearly, then 1 to 0 linearly, and so the average value there is going to be 1/2. When you do the math, you're going to see that a0 is equal to 1/2. Okay, so now we've got both pieces, right? We've got the k equals 0 term and the k not equals 0 term. So we have the entire answer using the differentiation property. So now I just want to kind of interpret our answer, and I want to point out that we do have the full answer now. So if you stopped, you'd be fine just specifying it like this. Okay, but let's try to interpret our answer, particularly this mess here. Again, just like the square wave, if you watch the previous video, the triangle wave only has odd harmonics. And that's because when you plug in the even values of k, the sine of k pi over 2 will be 0, and so you'll have 0 even harmonics. But let's look at a1, an odd harmonic. So if I plug in k equals 1 here, I've got 2 e to the minus j pi over 2 times 2 times the sine of pi over 2 over pi squared. Okay, that's k equals 1 term. So can I reduce this at all? I've got e to the minus j pi. E to the minus j pi is minus 1. So I'll put a minus 1 there. And then the sine of pi over 2 is 1. Okay, so that looks nice. And so this means that the magnitude of the first harmonic is equal to 2 over pi squared, and the phase of the first harmonic is equal to pi, or 180 degrees. Okay, and if we just make some comparisons, let's put in, how about minus 1? Let's look at the minus 1 term. So if I plug in minus 1 for k, I've got 2 e to the minus j pi over 2 times 0, interesting, times sine of minus pi over 2 over pi squared, right? So e to the 0 is 1, I've got 2, I've got sine of negative pi over 2 is negative 1. So this actually turns out to be negative 2 over pi squared, and so that means, again, that I'm going to have a magnitude of 2 over pi squared and a phase equal to pi, or 180 degrees. Okay, so, and of course we don't have to stop there. We can plug in a equals 3, a equals -3, a equals 5, a -5, and so on, all the odd ones. But the important point is that the triangle wave, this is a recipe to build the triangle wave. You take the first harmonic, remember omega 0 was pi over 2. So the first harmonic, you take the sinusoid oscillating at pi over 2 frequency, you give it an amplitude of 2 over pi squared, and a phase offset of pi, and then add it to, again, pi over squared, but with an amplitude of 2 over pi squared and an offset of pi. And then you add it to the third harmonic and the minus third harmonic, and what you start to see is, you get something like this, and you keep adding the harmonics, and then this thing will straighten out, and it will become a triangle wave.